Hello, what is up, and welcome back to L3.4 Part 2. We're looking at this diagram. All that we know is that this is an equilateral triangle, and CE is a line of reflection. I think we actually do know one thing more, because he then folded his diagram across the 2 points of intersection of the circles to construct a line of reflection. So we know that this A and B are across from each other, and this is the line of reflection. Is that enough information to know? I think that's enough information to know that this side folds over and lands on this side. That's kind of important for the whole thing. I don't know why they don't have that in the list. See, not only is C a line of reflection, but it's a line of reflection that makes the equilateral triangle fall back on itself. Anyway, with that information, we are trying to prove some things. There's 4 people that are trying to prove things. Person number 1 is Clarita. I wonder if I should be doing these in order. She's trying to say that it's an altitude. She's trying to prove it's an altitude. What would make it an altitude? If it meets at a 90 and touches the other vertex. So if it wasn't an equilateral triangle, that is an altitude. And Travis is trying to say it's a median, which means that it hits the middle of this other side. These are the same. And if it was not an equilateral triangle, oops, it's getting a little sketchy, a median would look like this. Some of these things might end up being the same thing if it's an equilateral triangle. We'll see. Tahani wants to say that it is a angle bisector. Up here. So this angle is getting bisected. How is she going to prove that these two angles are the same size? If they're the same size, then both of them added together is cut in half down the middle. And lastly, Carlos wants to say it's a perpendicular bisector. Which, if it was not an equilateral triangle, would look like this. So it doesn't necessarily go through that corner, but it might if it was an equilateral triangle. Okay, let's do it. Oh, before we go through this flow diagram, let's look back at how would we prove what we want to say. Where's Clarita? Clarita. Altitude. She needs to prove that one of the angles at the bottom is 90. This angle in here, CDB, or the other one, CDA. Either one. If she can prove either one of those is 90, and we can see from the diagram that it meets the other vertex, that's what makes it an altitude. Hits a 90, hits the vertex, she'll be good. Travis, where you at, man? Median, Travis. He will need to show that it hits in the center of this side, and so he'll need to show these are equal to each other. Okay, let's just do those two and we'll come back. Yoink. What did Clarita have to show again? Oh yeah, that they're right angles. Oh, that they're right angles? Well, then she will just need the fact that CE is a line of reflection, which will then tell us that CD and AB are perpendicular. Again, that's from what I was talking about earlier. Fold the triangle over. The only way that a line lands on itself, which they're saying it is a line of reflection, so this line must land on itself as it's folded over. Segment BD must land on segment AD. The only way that lines land on themselves after reflection is if they are perpendicular to the line of reflection. If that is a line of reflection, then CD must be perpendicular, or rather AB must be perpendicular to a CD. But if they are perpendicular, well, then that means these are right angles. If these are right angles, then ta-da! Well, we should also CD hits this vertex, which we could state separately, but let's just ignore that. But that's enough to ding. Nice little proof. Oops. Do I need to zoom out? That'd be lame. I don't want to zoom out. Thank you, Clarita. And then Travis needed to prove that DB is the same as AD, that these are the same lengths. But if CE is a line of reflection and this segment's landing on that segment, that means these segments are the same size. If they're the same size, well, it's the midpoint. D is the midpoint. If D is the midpoint, then these are congruent, and that's all he needs. Trav dog. See, this is way nicer than yesterday's. Look at this. Look how much care and attention I'm giving this flow diagram. It's flowing. Travis. Oh, that was a little sloppy. If you don't know what I'm talking about, you know what? Yesterday's not so bad. Well, it's bad. Today's looking better. Next, Tahani needs to prove it's an angle bisector. What will support her claim? Where'd it go? Angle bisector. Tahani will need to show that these two angles equal each other, which we can get if we know that they're congruent. It's kind of more difficulter. ACD, BCD, ACD, BCD. So those are the things we need to prove congruent. That's in the flow diagram right here. How do we get to that flow diagram? Well, first we have to prove that the triangles are congruent to get that those angles are congruent. How do we get that those triangles are congruent? That's CD is congruent to itself. That's the reflexive property. Shared side. And then these two angles, which are in these two triangles, the two side triangles, the left side and the right side triangles, these two angles are both right angles. All right angles are congruent. So we have same side, right angles, and then the outsides of the triangle are all congruent because it's an equilateral. That's side, angle, side, and so we can do it. Let's put Tahani in red. So she's the only one who actually needs the fact that it's an equilateral triangle. Specifically, we need AC and CB. These two are the ones we don't care about for this proof, but whatevs. But she also needs that it's a line of reflection. Because she needs to know that these are perpendicular to each other. Because she needs to know that these are both right angles. Let's add a step to this flow because Well, wait, it's down here actually. No, it's not. Never mind. We're gonna say that angle CDA is congruent to angle CDB. Yeah, that might seem obvious, but it's a slightly separate concept of the fact that they're both right angles. The fact that all right angles are congruent, therefore. Then this goes in here. This goes in here, I guess. So that's side angle. We need this other side to be established. We can do that if D is the midpoint, which it is because of the line of reflection going through D, which means that these two segments are congruent, segments at the bottom, AD and BD. Oh no, did I screw this up? I think I might have screwed this up. She doesn't need that, does she? Oh no. I forgot that this factoid that CD is equal, that's the other side. This just floats here. I don't know what this is. I don't like the way this is laid out all of a sudden now that it's made me mess up. Okay, we're going to do this like a Quentin Tarantino movie. We're actually going to go talk about Carlos's claim that it is a perpendicular bisector, because this will allow me to write over those red lines with purple lines. Because Carlos is going to be purple. Because she does not care that D is the midpoint. She only cares about the shared side, the 90s. Am I doing this right? Maybe I've double screwed up. That's super embarrassing. Okay, this is the bisector part that Carlos needs. Going this way. And he also needs that it's perpendicular. Where does that come from? Right here. Then we're going to have to get to the bottom of Tahani's claim. And I think that's it for Carlos. Come on down, Carlos. He needs two arrows, because basically his claim that it's both perpendicular and bisecting is based on these two claims, that's an altitude and it's a median. So he's getting two pieces of logic to come together. All right, back to I guess there's two ways. I'm confused because we have to use hypotenuse leg. Maybe they did this on purpose. This is a leg, this is an hypotenuse of these two triangles. Okay, here's what I'm thinking of. We know these are congruent because it's equilateral. We know these are congruent because line of reflection. And we know this angle is the same as this angle. So that's enough to use hypotenuse leg to prove that those two side triangles are the same. But we also know that this side is congruent to itself because it's of the same side. That's reflexive property. So which one do I want to use? Oh, I'm going to use hypotenuse leg. Though that is the one we studied the least. Well, it's the one that I can do the best on this diagram. So just to refresh, since we didn't use this one very often, if ignore the blue side. If we're using purple and red and the yellow angles, that creates the pattern that's not allowed of side-side angle. If you have two sides, purple and red, you need the angle to be in between them to use side angle side. The one exception is if it's a right triangle, but then if it is a right triangle, we don't call it side-side angle. That's the one that spells the naughty word backwards. We call it hypotenuse leg because it is a right triangle special exception. And unfortunately, that's the one we're going to use. So we got this feeding in here. Okay, finally, we prove that the two side triangles are the same using hypotenuse leg. If the two side triangles are the same, then these two angles are the same, CPCTC, which means that corresponding parts of congruent triangles are congruent. If these angles are congruent, then it is an angle bisector. Thanks to Hani, that was a lot. No, just kidding, I loved it. But we got there. Now, these little labels I put right here are a little clue for what we need to do next, which is work on adding justifications to each one of these steps in the flow diagram. Because right now we just have the flow of ideas, we don't have like why if you know that ABC is an equilateral triangle, can you then just suddenly state that the sides are congruent? Well, that's the definition of an equilateral triangle. Okay, well, we just need to explain that little step of logic. That is the definition of that. We have to pretend like we're talking to someone who doesn't know stuff. That's because at some point, how do you really know that the person you're talking to knows the stuff that you know? You don't. So starting at the baseline of assuming nothing, you go from there. So here's our list of stuff. Here's the definition of equilateral triangle. How about the fact that, here's that other little factoid that I was telling you about that we needed. 11. The book says 11 goes right here. Doesn't really make sense. Okay, but if CE is a line of reflection and combined with this factoid, we know that this has to be perpendicular. That is the definition of reflection. But if those two lines are perpendicular, then those two angles are right angles. That is the definition of perpendicular. 5. Definition of perpendicular. So see if you can go through your list and put some more labels on here. And I will see you in part 3.